Hello everyone, let's find out the electric field due to an infinitely long straight charged wire using Gauss theorem. So let's assume there is a charged wire which is infinitely long. So we put three dots at the two ends. This would mean that the wire is charged infinitely. Let's assume that this wire contains positive charge. As seen in the diagram to the left of the screen, we think it is charged positively. So from here the field lines would be almost parallel initially. So it will be like this. This is how the field lines would be on either side. So here we need to find electric field because of this infinitely long charged wire at a given point. So imagine that at this point P we should find the electric field. Again, as discussed in the previous section, the total electric flux is given as E into dA into cos theta, and then since Gauss law is true for a closed surface, we put a circle here implying the integration is over the closed surface. Now here, to simplify this or to make it easy to solve, we should choose a Gaussian surface such that the electric field comes out as well as this cos theta is equal to a constant or is equal to 1. So that depends on the Gaussian surface. To make cos theta equal to 1, we should ensure that at every point or at every small region, the angle between the electric field and the small area element would be 0. So the best fit surface here would be a cylinder. So in this case, we can consider a cylinder. Imagine that at this point P or somewhere here, we need to find the electric field. So we need to take a cylinder of a given length, because recall that this wire is infinitely long. So we should take a cylinder of a certain length only. Let L be length of the cylinder and let the cylinder radius be small r, such that the point P lies on the cylinder. Here we can divide this cylinder into three areas, that is the circular bases at the top and bottom. Let us call them as 1 and 2, and the curved path. So we have three surfaces. So the total flux here is equal to flux through the first surface, flux through the second surface, and flux through the third surface. But in each case, for each flux, the form remains integral of E into dA into cos theta, and this will be for the closed area, a complete area. Let's find them one by one. Let's consider. So consider surface 1. Surface 1. Now the surface 1 is like this, and if you take any small part on this surface, like here, for the small region, the area vector would go out like this. So area vector would be normal to that area, but the electric field is going like this. If you assume that somewhere here is the charged wire, somewhere here, then the field goes out like this. Or if you look at this part of the wire, the field goes out like this. So the angle between the electric field and area vector here is 90 degrees, and then cos 90 is equal to 0. Therefore the flux through the first surface is equal to it is E into dA into cos 90 is equal to 0. Similarly, if we consider surface 2, which is the bottom surface, even there also, if you take any small area anywhere, any small area, then the area vector is normal to that area element. So this would be dA, and electric field goes either like this or like this, depends on which part we're taking the area element. If you assume that this is the wire, and then the field would go out like this. Again, here also, as seen in the previous discussion, the angle between the electric field and area vector, which is theta, would be here 90 degrees, and then cos 90 is equal to 0. Therefore, flux through second surface is also equal to 0 by same logic. Let's do it at the side itself. Let's consider area 3. We'll do directly in the diagram itself. So in this case, if you look at any small elemental area, a small area here, now for this, the area vector would be normal to it, and also we saw that the electric field goes out. So at this part, electric field would go out like this, such that the angle between the electric field and area vector, this case would be 0. Similarly, if we look at any small area, at this point also the area vector would be normal to this. We'll call this as dA, and electric field also goes out in the same direction. So even here the angle between the electric field and dA would be 0. So with similar argument, we can say that if we take any small area on the curved part of the cylinder, for every small area, the angle between the electric field and area vector would be 0. And also the distance between the wire and cylinder, which is taken as R, is also same. So by that logic, for surface 3, then what we get here is the total electric flux through surface 3 would be integral of E into dA into cos theta. Now here E comes out because for any point on the curved surface area, the field would be constant in magnitude, and also for that part theta is equal to 0 and cos 0 is equal to 1. So what remains would be just integrating the total and integrating the curved surface area, and from geometry the curved surface area would be 2 into pi into r into L. Do remember that this means adding all the small areas. Imagine that if you have something of this kind, if you divide into small elemental regions, and if you take any one as dA, suppose this is like dA, and if we integrate this over the entire region, then what we get would be its total area. So here also, if we integrate all the small elements, then what we get would be the total area, which is 2 into pi into r into L. This is what is the total the area of the curved part, and the flux would be E into 2 pi r into L. Therefore, the total flux would be flux through 1, which was 0, and flux through second surface, which was 0, and flux here is E into 2 pi r into L. Therefore, the electric flux through this cylinder would be E into 2 pi r into L. We call it as 1. We obtain this expression by using definition of electric flux. Let's use Gauss theorem. So from Gauss law, what we get would be, by definition, the total electric flux through any closed surface is equal to charge enclosed by epsilon naught. Here charge enclosed means it is a charge which is contained in a cylinder. It's contained in region between A to here. Now we have seen in the previous class that for such kind of a charge distribution, we define a term called as lambda. So lambda is defined as charge by length. That would mean that charge is equal to lambda into length. So from this form, we get charge is equal to lambda into length. So length would be the length of the cylinder itself, because we are finding the charge in the Gaussian surface which is contained in the cylinder of length L. Therefore, this would be equal to charge was lambda into L by epsilon naught. We call it as 2. So let's compare 1 and 2. When we compare 1 and 2, what we get is, we get E into 2 pi r into L is equal to lambda L by epsilon naught. From here, L gets cancelled. It is common sense that L should not be in the equation, because length is what we taken. So it can't depend on the cylinder length. That is because, suppose imagine somebody had taken a small cylinder, somebody taken something of this kind. So the field at this point shouldn't change. That's the reason that L gets cancelled, because the electric field at that point shouldn't depend on length of the Gaussian surface. We studied this in theory part. Therefore, E from here is lambda by 2 pi epsilon naught into 1 by r. So this is the required form for electric field. In terms of vector quantity, E is equal to lambda by 2 pi epsilon naught into 1 by r into r cap. R cap means it is going out radially. The meaning of it. That is because, if you look at any part here, each part is like a circle. So each part is like a circle. Just think of this circle, and then the field goes out like this. So it goes out like this, which means it is going along the radius. So it goes out radially. Hence, it is given by r cap.